Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Dr. Antonio Lieto, who is a researcher in artificial intelligence and cognitive science at the University of Turin in Italy and a research associate at the ICAR-CNR Institute in Palermo. His research focuses on knowledge representation and automated reasoning, common sense reasoning, semantic and language technologies, cognitive systems, and architectures. On these topics, he has published more than 70 papers in international conferences, journals, and books. Welcome, Antonio.
So, hi, Gil. Thank you for this invitation.
Absolutely. You have been working on topics of common sense reasoning and more recently in computational creativity. These are possibly a few steps above what most people think about in artificial intelligence today, which tends to be more mechanistic, such as machine learning and deep learning. Could you describe what you mean by common sense reasoning?
Yeah, common sense reasoning is a research area. It's, let's say, an old and new area of research within the artificial intelligence field. Yeah. And it is based on all the type of reasoning that we humans are able to do very quickly. It concerns, for example, induction, abduction, and this sort of, let's say, common type of reasoning, but that is, let's say, common for us, but it is very difficult to model within machines. And I said that it was an old problem because it was, having machines able to model this kind of cognitive faculty was already a goal of people like John McCarthy or Marvin Minsky. And so this problem was already, let's say, there in the early days of AI. And now is returned because actually we didn't do a lot of progress in the last 60 years. So most of the methods of the current methods based on machine learning and or deep learning, this kind of stuff, are, let's say, used to perform not this kind of task, which requires, of course, reasoning and, let's say, different kind of ingredients, but they are mainly based on build better machine on perceptual task. So on learning things from the data, try to figure out some kind of regular patterns and try to make some kind of decision. So let's say that it's and in fact, for example, the methods that I use in my research are not based, for example, on deep learning. So I use symbolic methods or hybrid methods and hybrid architectures in order to achieve this kind of let's say, in order to deal with this kind of task in machines.
Okay. So when we think about reasoning, different types of reasoning, so deductive, inductive, and abductive reasoning. So are you seeing common sense reasoning sort of a superset of that, or is it different?
I would say that common sense reasoning is concerned mainly with the induction and with the abduction. But it is, let's say, not a kind of, it is a particular kind of induction and of abduction. It is a kind of inductive inferences and abductive inference that are common, so that most of the people can do, let's say, in a matter of seconds, for example. Okay. So there is this typicality effect, which is a crucial part. So it's the kind of reasoning that we are used to do, and that requires a lot of, let's say, implicit knowledge that we have as humans about the states of the world, but that we are able to put in place when very quickly when we have to make some kind of, let's say, real life and real time decisions.
Okay. And so when you say symbolic methods, what do you mean?
Well, the symbolic paradigm is somehow, let's say, antithetic with respect to the current machine learning and deep learning techniques, because, I mean, in the history of AI, the two main modeling paradigms that have been developed are the symbolic methods, which assumes that the information, let's say, in the mind, okay, in the software of the agents, should be represented as symbols, which are somehow a proxy of objects which are over there in the world. And in this way, this kind of abstract symbols can be used to be combined among them, and can be used to solve problems. So if you see a problem as and you formalize a problem as something that is a symbolic problem space, solving a problem in this kind of situation could just mean that you have to minimize, let's say, the distance between two symbols, an initial symbols and a goal symbols that are, let's say, within this kind of problem space. So it's all the for example, logic-based frameworks, which are developed in artificial intelligence, are developed based on this kind of symbolic assumption. So every logical formalism is composed by symbols of the alphabets and some kind of operations that you can carry out in this kind of, let's say, structure. And of course, these symbols have a clear and specified semantics, and you can reason on this kind of symbolic structure. So that's the whole point. It is completely different with respect to the connectionist agenda, where you do not have a symbol that has a meaning of, let's say, a particular concept. You do not have a symbol resembling, for example, a cup of that is associated to a cup of coffee. But you have patterns of connections within the artificial neural networks that can somehow together form, let's say, the distributed meaning of what a cup of coffee is. So there are two completely different modeling approach to the way in which the information is structured within, let's say, the mind, okay, of artificial agents.
Okay. So let's dig deeper into some of your papers. You had a paper in the Journal of Experimental and Theoretical Artificial Intelligence, and it's entitled Dual PECs, a Cognitive System for Conceptual Representation and Categorization. And you present in that paper a cognitively inspired knowledge representation and reasoning system aimed at extending the capabilities of artificial systems in conceptual categorization tasks. You want to talk a bit about that?
Yeah, I mean, in this system, in the system that is described in this paper, this is a system developed with some colleagues of mine at the University of Turin, Daniele Radiccioni and Valentina Ro. Well, we have implemented a system that is able to perform as we humans do, to perform and to integrate different kinds of categorization types. So we as humans are able to perform not only, let's say, a simple form of categorization when I assign, let's say, by following specific rule, a data point to a particular class, let's say, but we are able to perform different kinds of common sense categorization. So, for example, I can say that a particular instance is a dog if I, let's say, am able to recognize the features that this element, for example, is able to hoof or as four or as four legs, right?
Yeah.
So, but all these features are common sense features. So this kind of reason, this kind of categorization is an example of common sense categorization because all these features are neither necessary nor sufficient for defining something like as let's say belonging to the category of dogs. But nonetheless, we commonly do this kind of inferences, and most of the times we are right because this kind of inferences can be considered as a sort of shortcuts, as a sort of heuristics that our minds uses in a very effective way in order to, let's say, survive, let's say, in an environment in which we do not have a complete information about the world, in which we have to deal with the uncertainty and this kind of stuff.
Okay.
And this system was, I think, interesting because it introduces, it is based on two main assumptions. So the first assumption is that in artificial system, we should assume that all the concepts which are, let's say, dealt with within this system should have different kind of representation. So we may have multiple representation of the same concept, and this is something that is also grounded on, let's say, the cognitive science, on, let's say, human cognition literature.
Right.
And the second assumption is that on this kind of different kind of representation for the same conceptual entity, we should be able to model different kind of reasoning, a sort of common sense reasoning of the type that I have described before, and some more, let's say, classical types of reasoning. We just follow some, let's say, explicit rules in order to assign, for example, an instance to a data point to a given category. Okay. And so this is we have integrated in these systems in this system dual packs this kind of assumption, and we have compared our results with what the humans, the human let's say responses to, let's say, the task of common sense categorization. We have obtained let's say quite a good overlapping.
Yeah. So my understanding, Antonio, so if I think about categorization, and correct me if I'm wrong, I could envision sort of a spectrum of methodologies that I could utilize. So on one side, I could use something like a deep learning neural network that uses a different way to categorize things, and it tends to be very brittle. Because it's only capable of understanding what it has seen, and really not able to reason very well. On the other hand, I could actually write a rules-based system, and if I write an infinite number of rules in that system, presumably I will get a good performance from that, but it's very manually intensive, very expensive. So if I understand this correctly, will common sense reasoning sort of fall in the middle?
I Yes, sort of, in the sense that, for example, with neural networks, you can also obtain some kind of, let's say, some instances of, let's say, associative reasoning, which is part of the common sense reasoning, and this is something that this class of system do quite well. But for example, we are not able to tell why you have obtained this kind of results. So one important feature of let's say common sense is that it should be the kind of inference that you draw is for the humans at least, something that you can easily, let's say, also explain. Now, within the, for example, dual PEX system, we use the hybrid architecture.
Yeah.
One which the first part dealing with common sense categorization is based on a particular type of vector space model. And if you want, you can interpret, let's say, the last layers of these deep networks as a huge, let's say, as huge vectors, right?
Yeah.
So in this sense, let's say there is the link with the connectionist and with the sub-symbolic part. But the other things that you're able to do is to, with the help of the, let's say, the symbolic part, which is connected with our vector space representation, is, for example, to explain some particular type of errors. For example, if I want, a typical example is this one. If I want to categorize let's say, linguistic description of the type, which is the enormous fish that eats plankton, okay? Well, the first type of, let's say, categorization result that comes out immediately to our mind is probably the answer whale, okay?
Yeah.
Because whales are typically associated with all the main feature of the category fish, category of the fishes. However, we know, let's say that whales are do not belong to the category of fish.
Yeah.
They are mammals, right?
Right.
So this kind of, let's say, check can be done within our system, and our system can suggest to select, let's say, another most appropriate, let's say, associative answer that comes from, let's say, the first common sense category, because the first one is obviously wrong.
Okay.
So I think that this is something that is this kind of, let's say, communication between the fast type of reasoning, the common sense reasoning, and the more logical reasoning that we have in dual PEX is something that is missing in all the current deep learning architecture. So we have just, let's say, the fast type of categorization, and which works, let's say, pretty well in many types of examples, but it, of course, have also some additional problems.
Okay, so could you talk a bit about the mechanics? Then you say, the hypothesis of conceptual structures represented as heterogeneous proxy types. So is the system utilizing neural deep learning networks at some level, and then you have some sort of a hybrid reasoning around it? Is that how it works?
Well, the heterogeneous proxy types framework that I developed is somehow, let's say, sort of agnostic with respect to the modeling tools that you can use in order to model this kind of mechanism within an artificial system. So in our case, we developed a linguistic-based categorization system. So we were able to, let's say, have this kind of dealing with this kind of linguistic stimuli, and we decided to go with the hybrid architecture combining vector space model and symbolic models. But of course, instead of the vector space model, if you want to, for example, use the same kind of heterogeneous proxy type approach, for vision, you can, for example, substitute the let's say vector space model component with a deep learning architectures, because we know that we can obtain better results by using that kind of tool. So in general, the heterogeneous proxy types hypothesis is based on the assumption that once we receive a perceptual stimulus to categorize, it can be, let's say, a visual stimulus or can be, let's say, linguistic type of stimulus. What we do is a sort of comparison, similarity-based comparison between the stimulus and the kind of representations that we have in our long-term memory.
Yeah.
And what is selected is, and let's say, within this selection, there are different kind of heuristics that are used. When something is selected as, let's say, the most similar representation with respect to the stimulus that you want to categorize, we, let's say, make this representation proxy within the working memory of our, let's say, artificial agent. So we assume that there is a memory system within, let's say, an artificial agent that is based on a long-term memory, which stores all the informations, and a working memory, which is a sort of buffer. You can, in computer science terms, you can, let's say, things to the working memory as a sort of buffer. Yeah. And this process explains which are the mechanisms for, let's say, selecting, let's say, the appropriate representation which are selected as a proxy in working memory. Of course, once you have a proxy representation in working memory, you can then use the kind of representation for doing other kind of, let's say, activities like planning or multi-step reasoning or this kind of stuff, or making an action. If you let's say, use this kind of architecture within a robotic system, let's say, and an important issue will be that one of making a decision for making an action.
Okay. So build up the long-term memory. The inputs are both linguistic description as well as visual description. So there's a variety of different types of information that's being used.
In the original, in the work that is described in the paper, we were able to deal with linguistic descriptions in English and let's say in a bunch of other languages. This kind of descriptions, so it was a sort of, let's say, question answering system that was able to deal with the common sense type of questions, okay, which are the most difficult ones to handle. We are now, so this was the original paper. We are now extending the architecture with the goal of trying to let's say integrate also visual the vision system. Okay. Actually. We have some hints about how to do that, because, for example, in the original paper, we were able to integrate the two different kinds of representation that we use by using let's say, a symbolic representation, which are based on ontologies and semantic networks, and the vector space representation were grounded together via WordNet, which is a, let's say, quite well-known linguistic resources. So we had actually WordNet that was used as, and that is used as, let's say, a sort of linking layer between these two different co-referring representations. They are co-referring because basically, as I mentioned, they provide different views, a common sense view and a classical, let's say, view on the same kind of concepts. So, for example, I can say that for the concept of water, I could say symbolically that water is every item that is formed by two atoms of hydrogen and one atom of oxygen, right? Mm-hmm. But from a common sense view, I do not use that kind of conceptualization in order to deal with, let's say, real world data. So, for example, I can describe the water in a common sense way, and I can say that well, a water is something that is usually in a liquid state, it is colorless, and it is odorless. Okay. So, as I mentioned, as in the case of the dogs that I was mentioning earlier, all these three features are not necessarily sufficient for being a water, but this is the kind of features that we use in order to make fast associative types of reasoning. So we do not use the information about, let's say, the atomic components of the water. So this is just to give you an example. And as I mentioned, we are trying to extend this kind of architecture to the vision by substituting, for example, WordNet with ImageNet, which is, let's say, which can be probably another kind of huge data bank that we can use in order to connect different kinds of representation. But we have, let's say, for the moment, no results. I mean, it's a work in progress.
Okay. So in the original work, when you use, to take that example of that water, for example, the features, the common sense features, is there some level of importance given to those features during the training process, or it's all captured differently?
You mean how do we?
So whether it's a liquid, it's colorless, it's odorless. Let's say that those three features. Is there some level of ex ante importance assigned to those features?
Well, actually, the importance can be somehow extracted, because so it's not something that you put, let's say, manually within this kind of representational system. But if you look at how, for example, water is described, okay, by the people, they use this kind of description. So one way that you can have in order to extract this kind of typical feature is trying to let's say, figure out which are the most common kind of characterization for describing a given entity. And within this kind of let's say, characterization, you are going to find some typical descriptions for the kind of concept that you are looking in.
Okay.
That's I mean, there are a lot of projects also that have been around for a while. For example, the Open Mind common project at MIT, where the people were asked to annotate with a very, let's say, few features, thousands and thousands of concepts, and you can see that there are statistical regularities between the let's say, the features that are considered more typical for representing some kind of concepts, and you can just select that one.
Okay. And you also mentioned here that it may be plausibly applied to different general computational models of cognition. This is an original paper. Are you making progress in that direction as well?
What we did with this kind of architecture, I mean, we started to develop it from scratch, but we then started to realize that this kind of architecture was actually able to extend, let's say, the knowledge processing capabilities of some kind of cognitive agents, and it could have been integrated within already available cognitive architectures. Now, cognitive architectures are, let's say, a software instantiation of cognitive theories, and this is a field that started with Alan Newell in the let's say, late 80s of the last century. So we started to integrate actually our system within, for example, the ICAR architecture, which is a cognitive architecture developed at Carnegie Mellon University. We have also integrated this kind of architecture with LIDA and with SOAR and other architecture. So we actually showed how our extended categorization capability could have been actually plugged in within different kind of agents architectures. So in this way, the agents that were equipped with this kind of architectures could also, let's say, have the advantage of using our extended categorization capabilities.
Okay. Yeah, I want to jump into another paper which is related again from the Journal of Experimental and Theoretical Artificial Intelligence. It's entitled "A Description Logic Framework for Common-Sense Conceptual Combination, Integrating Typicality, Probabilities, and Cognition Heuristics." So you propose a non-monotonic description logic of typicality, able to account for the phenomenon of the combination of prototypical concepts. You want to talk a bit about that?
Yeah, this is a work that I've done with Gianluca Pozzato at the University of Turin.
Yeah.
And well, it actually tries to address a specific, let's say, question within the common sense reasoning research agenda, which is how are we able to, let's say, generate autonomously new knowledge, okay, by starting from the knowledge that we already have. And of course, how can we, let's say, create an automatic procedures that allows also an artificial system to automatically generate new knowledge to solve, for example, some new goals.
Yeah.
And our answer was that, well, actually, most of the, let's say, ordinary knowledge invention, so I mean knowledge invention which is not related, for example, to mathematical theories or something like that. So, but let's say common sense knowledge invention is based on reframing, on a creative recombination of the things that we already know. And a typical example here is that one of object composition. So, for example, let us assume that we want to invent a new kind of object. Well, if you want to do this kind of this task is a very difficult one, by the way, because only humans and a few other primates and the ravens are able to do this kind of are able to invent new objects by combining, let's say, other objects that they already know. So these are very, let's say, difficult task within the biological species and also within, let's say, the artificial intelligence research field. So, well, in this way, what we do is usually try to figure out, so we have a goal to solve. For example, we want to create an object which is graspable and that is able to launch other objects at distance, okay? But we do not have, let's say, within our knowledge inventory an object that alone is able to perform this kind of to satisfy this kind of goal. So what we suggest with this logic is that we can recombine in a creative way the things that, let's say, the inventory of objects that we have in our, let's say, in the artificial, let's say, mind, okay, of our agent, in such a way that the agents can, for example, invent a slingshot by combining the concept of branch with the concept of rubber band. Okay, so this is something that we have tested extensively, and this is actually the kind of work that our logic is able to do. So this logic assumes that actually most of the knowledge invention procedures that we do in an ordinary way are based on the creative recombination of the things that we already know, and it provides actually a framework that integrates, let's say, different kind of ingredients in order to perform this kind of task.
Yeah, it's very interesting, Antonio. I don't know if there's any connection here, but it has been suggested that when we dream when we sleep, when we dream, it's really a goal generation process by the brain, really combining information it has, creating a new goal in an effort to train, train the brain for future future encounters on things that it hasn't really seen yet. So it's sort of in the same vein here, right? Yeah. Go ahead.
I mean, absolutely. I mean, this is the main point. I mean, also, dreaming is, let's say, a process that within which there are a lot of, let's say, creative processes going on. And one of these processes is exactly this one. So trying to recombine, to reframe the knowledge that you have in order to, let's say, for example, be prepared for let's say some next goal that you are going to figure out within our dream, or something that you fear to face, or something something like that. And in general, I would say that also within the area of computational creativity, so within the area that actually try to build machines that are creative in both, let's say, the ordinary sense that I'm, let's say, talking about here, but also in the artistic sense. Okay, so in the artistic domain, one way that is described, for example, in the famous book of Boden about computational creativity. So she points out how there are at least, let's say, two different types of creative processes. The one is combinatorial creativity, which is the one that I'm talking about here, and another one is transformational creativity, which requires, let's say, some kind of additional steps. But I think that in most of the cases, so for example, inventing a new object, it may seem something that is, let's say, quite obvious to us, but it was not obvious at all from an evolutionary point of view. So having the capability of reasoning in this way is important, because most of the let's say ordinary let's say types of creative things that we do are exactly based on this process of common sense concept recombination, which is described in the TCL logic. What I can add is that the interesting thing is that we have actually applied our logic to, let's say, specific within specific knowledge-based application. For example, we have applied our reasoning system within the context of RaiPlay platform, which is the main. I mean, Rai is the main national broadcasting company in Italy. They have a huge online platform which is called RaiPlay, and we have used, let's say, our reasoning system in order to generate, for example, novel genre categories. For example, by mixing the genre of the thriller and the genre of I don't know, romantic series or romantic movies, something like that. Okay, in order to create, let's say, novel kind of hybrid genres, and in order to reclassify the whole content of their catalog. And this kind of reclassification has also been used in order to recommend to the users, to the real users of the platform, let's say, the content reclassified in these novel generated categories. And I mean, at least for now, we were quite successful. We have a paper that is forthcoming, that is presented that has been accepted in the ICAI conference, which is the main European conference on artificial intelligence, that has been done in collaboration with people from the technology center of RAI. So we have a real application within the context of, let's say, computational creativity and serendipity-based recommendation, which is actually based on these logic that is able to recombine in a creative way, as we humans do, new, let's say, different kinds of existing categories in order to form new categories that can be used for a variety of tasks.
Yeah, I can see mechanistically, Antonio, the combinatorial creativity. So, it is something that can move forward, I would imagine, pretty fast. But the transformational creativity is different, right? So, is it something along the lines that you're making random searches away from what you know in a design space and randomly find something? What exactly is transformational creativity?
Well, in transformational creativity, actually, you do not use just this kind of let's say combinatorial mechanism. So you need something more,
Yeah.
let's say, in order to I don't know, invent, for example, new concepts. Or in order to generate new, for example, I don't know, artistic styles or something like that. And it makes sense because it is clear that let's say our kind of creativity is not just combinatorial.
Yeah.
But I would say that most of our, let's say, common sense creativity is combinatorial. But for example, this kind of creativity is not exactly the kind of creativity that, for example, Caravaggio or Giotto may have had when they invented new kinds of styles. So they also had to somehow not just to were asked also for a kind of transformation of the space of conceptualization, let's say. Okay, so not just recombination, novel creative recombination within the same kind of space, but in some cases you also need to let's say change the space,
right?
And so this requires an additional step that for the moment is let's say out of the scope with respect to our law. I mean, we are aware of this kind of let's say this kind of literature, but our result was really, I mean, our aim was really that one of trying to provide some results in within this kind of combinatorial based, a common sense based creativity, which was still let's say a completely open problem within the artificial intelligence research. So this was not a, let's say, solved problem. And also in our case, we are happy with what we have, but we are trying to let's say build more efficient mechanism in order to obtain the results that we have. So I mean, there are still a lot of space for improvement.
Yeah. So I want to explore a bit with you, Antonio, sort of the philosophy of artificial intelligence. When I was in graduate school in the mid 80s, we were creating expert systems, what was then called expert systems. My thesis was one of those systems that attempted to teach graduate students to build up design intuition faster by interacting with computers. So, early work in this area, we used to think computers are actually a lot better than humans. We deployed computers to teach humans. And we have come a long way from there. But artificial intelligence generally seems to start from a point that assumes the human brain is actually very good, and in an attempt to replicate that in ways that we could. But very practically speaking, we don't really have a lot of information that says the human brain is the most efficient way of processing information or even creativity. In many business contexts, this is some work that I did in the mid 90s in a pharmaceutical company. we can demonstrate that human decision-making processes are faulty, and we see that in financial markets. And so from a philosophical perspective, is it a really good way to think about that? We almost without question assume that the human brain is probably the best thing we should attempt to replicate. Is that a good way?
Well, I think that one of the say particular say features of natural system, not just of the let's say of us as humans, is that we are able to perform simultaneously a multitude of tasks. Okay, within the same, the very same. Let's say hardware, which is our brain architecture. Okay, if I can use this kind of metaphor.
Right.
I would say that if you consider not just specialized tasks, like for example face recognition, okay, or like for example machine translation from I don't know English to Italian, okay.
Yeah.
Well, if we do not consider only very brittle and specialized tasks, we are still the best species in the let's say in this planet that are able to perform a variety of tasks in a satisfying way. I'm using this term a la Herbert Simon. So this term was introduced by Herbert Simon, which was one of the AI pioneers, but he was also Nobel Prize in economics for his studies on the bounded rationality. Okay, yeah. So he actually pointed out that we are not, let's say, optimizers.
Right.
Okay, we do not make optimal decision making because we are not able to. So due to our brain limitation and to our memory limitation, this kind of stuff, we are not able to calculate, let's say, the optimal decision.
Optimal decision.
Yeah, exactly. Yeah. For every and each decisions, but we use a set of heuristics. So these heuristics are, in most of the cases, evolutionary shaped. So this means that they are the best shortcuts for solving a given problems. And for example, common sense reasoning, just uses is just a let's say huge variety, a collection of let's say evolutionary shaped heuristics that enable us to make in let's say very few in a very fast way, allows us to make complex decisions, if you want. Okay, so decisions that machines are not able to perform in a matter of let's say seconds or milliseconds or something like that. Okay, so I think that if we, let's say, zoom out a little bit from some specific competencies, we can still say that we are still, let's say, the best system on this planet for a variety of tasks with respect to other, let's say, species, and also with respect to, let's say, the currently available, let's say, AI systems.
Yeah, so that is true, Antonio. I agree with that. But so we don't yet have a theory of consciousness. The broader question I'm wondering is, we seem to marvel at the human brain, and it does a lot of interesting things. And as you say, it has heuristics that, it has an operating system. Those heuristics over 50,000 years. Built into either the operating system or apps put on that operating system. Those heuristics also have a lot of errors in them. So there is an architecture question, and there is a sort of a software question. And I think our hypothesis appears to be that is the best way to optimize, not necessarily to optimize, to reach decisions. Now, if we say that the objective function, the goal, is to optimize, then we shouldn't really be starting at the brain architecture nor its processing methods, right? because input doesn't do it. Yeah.
I mean, as you mentioned, I mean, if I understood correctly your point, I mean, as you mentioned, it depends from the kind of goal that you have when you want to, let's say, build a machine. For example, a typical example is this one. There is in the influential textbook on artificial intelligence by Russell and Norving. They famously stated that the quest for artificial flight succeeded when the Wright brothers and the others stopped imitating birds and,
right.
and started using wind tunnels and learning about aerodynamics.
Yeah.
So this is the point. But this is true because, for example, from an engineering perspective, if you want to just build, let's say, a better technology that is able to perform that particular kind of task in a better way. So probably, let's say, the natural inspiration, not that one coming from humans, but also from other, let's say, biological species, can be somehow misleading, and you have to follow different, let's say, principles.
Right.
But I would say that if your let's say if your goal is that one of trying to build a, let's say, cognitively inspired or a biologically inspired system, you do not have just this kind of, let's say, technological goal. You also have another kind of goal, which is that one of trying to use this kind of simulation in order to explain something that is still not clear from let's say, neuroscience point of view or from a psychological point of view about how the brain works and about how the mind works.
Yeah.
Okay. So you, in this case, you have a twofold goal. You do not just have the goal of providing let's say, better technologies, because in some cases it can be completely let's say, unhelpful to have this kind of human inspiration or cognitive inspiration, but in general to have a naturally inspired approach. But if you want to build also models that have some kind of explanatory role, well, you actually need to build this kind of models. And the interesting thing is that in some cases, not always, but in some cases, this cognitively inspired AI system or the biologically inspired AI system also achieve better performances in the context of, let's say, of the strictly speaking AI technological domain. So it means that there is something, okay, that it is worth considering in the design of intelligent system that comes from the how, let's say, how our mind and
we
our
do it. Yeah.
Yeah, exactly.
But would you say, Antonio, that we are really focused on sort of what I would call the micro, the individual, right? The goals of an individual brain. But there are potentially larger questions around societal conscience, how humans interact with each other. And so when we take an engineering view to artificial intelligence and conscience, it seems to me that, there might be other ways to think about it. I don't know a lot about it, but, it's a very mechanistic micro view of how the brain works. Perhaps, the brain is sharing information in ways that we don't quite understand.
Yeah, I mean, for sure, this is a crucial point. I mean, currently we do not know that much about the brain. Okay, so even if it seems that we are making a lot of progress, but actually we are very far from understanding also the most fundamental, I would say, let's say, a mechanism of the brain about, let's say, not just about high-level cognition, but also about motor coordination and, let's say, a lot of other stuff.
Yeah.
So it is possible that we are assuming a sort of micro perspective, but it is just I would say
it's a place to start.
Yeah, exactly. It's the best. I mean, it's the best that we can do right now, because we are in the dark. I don't know how to say, but that's true. I mean, that's true. I mean, also people working with a lot with neurosciences. I mean, I have a lot of interaction with them. I mean, we are really in the dark. In the neuroscience literature, you can find for the same kind of, let's say, fMRI studies, completely opposite explanations. So it's really difficult to understand also and to interpret the results that they are starting to obtain with, let's say, with for example, fMRI studies or other kind of neuroimage based studies. So this is, as I mentioned, just a way to start. I agree with you that probably, I mean, we are, I mean, we don't know where we are, but this is just a starting point, I would say.
Yeah, it keeps us interested. So, Antonio, in conclusion, I want to ask you, if you look forward 5 years, where do you think we will be in artificial intelligence more generally?
More generally, you mean on,
you know, in terms of I should say, in terms of applications, you know, where do you think, where do you think we will be in 5 years?
I think that there will be still some let's say narrow improvements in areas like, for example, natural language processing, with the use of let's say these language models like GPT-3 and so on and so forth. There will be a lot of applications that will be built on this kind of models, and probably some minor let's say some minor advancements also in the field of vision and speech and so on and so forth. So I can see this coming in the next 5 years. I cannot see, let's say, an integration of all these different kinds of, let's say, distributed faculties. We still do not know how to integrate, also in a kind of, let's say, naive way, okay, all these kind of, let's say, intelligent faculties within an artificial system that is able to, let's say, achieve, I will not say human level performances, but let's say acceptable performances. So we are, there is still a long way to go.
Yeah, and this is an area that you're pushing forward, sort of integrating linguistic, visual, and other types of inputs. Those systems, I think, tend to look at it sort of a disconnected way. But I think your approach might be going in that direction of integrating them, right?
Exactly. This is exactly the point. I do not consider the construction of single systems as a sufficient mean to enable the generalization of, let's say, unifying systems. And one way that I suggest to follow, and it's not only me, of course, there is an entire research community, is that one of trying to figure out which are the possible cognitive architectures, so which are the invariant structure of human cognition that we can build within, and that we can, let's say, instantiate in a software that enable us to have, let's say, a sort of common ground upon which we can build vision applications, speech applications, linguistic application, and so on and so forth. Of course, this is a very difficult task. That's why, let's say, in this context, there are no, let's say, very huge successes. So it's easier to go, let's say, to divide, to use the divide and conquer approach, right?
Right.
But I mean, I think that from a scientific point of view, it is also interesting to trying to figure out how we can really integrate this kind of aspect, because this can also have a lot of impact in the area of concrete applications.
Yeah, excellent. Yeah, this has been great, Antonio. Thanks so much for spending time with me, and good luck with
Thanks.
all your research.
Thanks. It was really a pleasure. Thank you very
Thank you.
much.
Bye.